So today I'll be talking about a model of forest succession, and before we begin on talking about the model, we must first talk about forest succession. Forest succession is a process of change of species composition. It follows a predictable pattern from grasses and weeds to mature forests, and this process of reaching mature forests can sometimes, and usually takes, many centuries. So if you look at the picture below, you can see that there are several different stages. Now each of these stages would represent different species compositions. So you're changing species compositions as you progress through the years. And it's following a predictable pattern from plants to a mature forest. You'll notice also that they have given the timescale for reaching this final stage about 150 to 300 years, in other words, several centuries. So now that we have figured out a little bit about forest succession, we can begin talking about the model. Here's the flow diagram I have created for my model. So we have four different stages. We have pre-successional, S0, stage 1, or primary successional, S1, secondary successional, stage 2, S2, and tertiary successional species, S3. Now you'll notice that exiting from each of these values to the top is a alpha. This alpha is the rate of catastrophe, which would be things like fires or volcanic activity, etc., that might cause plants in that stage to die. And this would essentially reset all the progress back to pre-successional. You'll also notice that there are two arrows going between each of these stages. On the top arrow, the beta, gamma, and delta, is the rate of change from one species, successional species group to the next. And the term on the bottom is the rate of increase of this rate of change. So this would be, say, if you have an ash tree in a plot, this would say that ash tree would increase the colonization of more ash trees because it is dropping seeds in that plot. Now, at a certain point, the amount of ash trees that are in that plot would no longer increase the rate of colonization, and this saturation point is the A value in that equation. Another thing to note about these variables, these are all proportions of plot area, so all four of these stages must be less than 1, and they must add up to 1 and if you add all of them together at any given instant in time. So now we can begin looking at each of the equations, since I've already talked a little bit about what each of the parameters mean, I won't go into that too much here. So here we have the equation for S0, the pre-successional species, such as grasses and weeds. Now you'll notice that this is a recursive equation, not a continuous equation. Now this is because plants are annual reproducers and they grow during a certain growing season. So it does not make much sense to model them continuously as if they were to grow throughout the year and reproduce throughout the year. So here's the equation for the primary successional species. These would be things such as bushes and shrubs, and you'll see you have the inputs as the rate of change and rate of increase of that change, and the outputs going to stage 2 as the rate of change from stage 1 to stage 2, the gamma, and the rate of increase of that change. You'll also see the alpha value exiting. And once again, this is also a recursive equation. Stage 2 is much the same, you just have different parameter names, as these are different rates because you're going from stage 2 to stage 3. Now stage 2, or secondary successional species, would be things such as coniferous or softwood trees. These would be pines or fir trees. Now stage 3 successional species, or tertiary successional species, would be things such as deciduous or hardwood trees, such as oaks and maples. Now here, since this is the final stage of succession, there are no rates of change to the next stage. And you'll also once again see the rate of catastrophe exiting. So now that we've looked at the equations a little bit, we can look at the parameters and their relative sizes. I'll particularly direct you to the beta, gamma, and delta values. These were the rates of change from one stage to the next. Now beta was the first rate of change. It was from pre-successional to stage 1, and you'll see that it is the highest. Now this is because it is assumed that stage 1 successional species will colonize the area first and the fastest. And likewise, you'll see that the rate of change for stage 2 to stage 3 is the slowest, as these will take the longest to colonize and the longest to appear. Also, you'll see a similar trend in the A values, which is the maximum rate of increase of the change. The A01, which is from pre-successional to stage 1 successional, is the largest, and the A23, which is from stage 2 to stage 3, is the smallest. Now, in order for this model to work, there were various assumptions that were made. I've mentioned some of them before, but I will now explicitly state them. Tertiary successional species are assumed to be the highest stage of succession in this plot. Furthermore, individual species are not being modeled, but rather the groups of species that they fall into, such that they create 3 categories, or 4 categories. These 4 categories. So you could create more categories if you wanted to. You would just have to reflect that in the equations that were created. Also, the rate of catastrophe is assumed to be the same. That's the alpha value, regardless of the stage of succession. Though it is still dependent upon each stage of succession that plot area is in. So now we can look at how this plots out on a graph given those parameters. So here you'll see the 4 lines, the 4 different stages, the red being the pre-successional, blue being the primary, purple being the secondary, and orange being the tertiary. Now if you'll look at time equals 0, there are only pre-successional species present, so the initial conditions would be 100% pre-successional species. Now if you look at, say, time equals 15, particularly at the orange line, the tertiary successional species, you'll see that tertiary successional species are beginning to colonize the plot. Well, that might be slightly confusing for you, seeing as how I said that tertiary is the final stage, and the final stage of succession in those diagrams at the beginning were at 50 to 300 years, and this is 15 years. Well, you must think about this as this is just when they are appearing. This is not to say that they are a certain height or that these trees have matured. So these values are just saying that they are present, not that they are mature and fully grown. So it could take another 50 to 100 or more years for a mature forest to emerge, even though the first trees are appearing at that 15-year mark. Now we can look at a larger time scale, particularly to get the equilibrium points at the end where everything seems to be leveling out. Now the pre-successional species, they seem to be leveling out at a 5% occupancy of the plot area. The primary successional species appear to be at about 10%. The purple line appears to be at about 15%, and the yellow-orange line appears to be at about 70%. Now an important thing to note is that this succession is not an all or nothing process. So just because you're going from stage 2 to stage 3 doesn't mean that all of the stage 2 species are completely eliminated in the process. So at the end there are some percentages that are present for each stage still. And here are these equilibriums again, just written out. Now it's important to note that these were for the rate of catastrophe, the alpha value of 0.005. If we were to change this value, these equilibriums would change quite significantly. If we were to increase this alpha value, the tertiary successional species would occupy a significantly less portion of the plot area. So now that we've modeled and seen how this plots out graphically, you might be wondering, well, what's its pertinence? What can this be used for? This model could be used to determine, say, how long it might take to return a deforested area to its previous standing of, say, a mature forest. So if for whatever reason a fire just completely devastated an area of land, if you knew some information about it and where it was before, you might be able to determine how long it might take to get back to that point. And maybe a more pertinent and easier to understand application of this would be, well, if if you were, say, a logging company, you might want to determine how much you can uh, harvest from a forest before you destroy the forest. So if you're a logging company, you want to keep the forest alive so you can continually have something to harvest and not have your company go out of business. Well, you could use this model and manipulate the amount of catastrophe to determine at what point you might disrupt the balance and destroy the ecosystem. And you could do this by, say, setting a threshold value for each of the stages of how much of the plot you want occupied by those various stages. So hopefully this gives you a little bit of insight into forest succession, and I hope you understand my model. Thank you.